refresh our memory on a couple of things. One is that when we have a logarithmic expression with a base that is the same as the exponential expression that's nested in it, that those two things cancel out. That inverse property cancels the two things out, and we're left with just x. Okay. So we will use this property as well as the power rule. Recall that when we have the log of something raised to a power, we can take this power and let it function as a coefficient of the log. So this expression log of 28 raised to the x can also be written as x times log of 28. Okay, so we're going to use both of those things to solve some problems. I'm going to start with this example of log of 84 raised to the x is equal to 70. Okay, so there's a couple of different ways to approach this. I'm going to show you two, and you can see what sounds good to you. The first thing that I would say is the way I would personally approach it, and that would be coming back down to this concept. I see I have an x in my exponent, and I want to get that x by itself. So I can take a log of both sides of the equation, but I want to take the appropriate log. So one way to do that would be to take a log with a base of 84 on both sides of the equation. And when I do that, I've created this thing that cancels out, leaving me just x, right? Because when that base of the log and the base of the exponent are the same, then they cancel each other out. So I get x is equal to this log base 84 of 70. And I'm going to rewrite this using change of base so that I could evaluate it using my calculator. So I'm going to use a common log. Log of the argument over log of the base. Okay, this is an exact answer. When we use our calculator, which we should as well use our calculator to get some kind of approximation, realize that it is an approximation. It's not exact. It's like saying 0.333 is the same as 1/3, and well, they're really close, but they're not exactly the same thing. So let's go ahead and use our calculator to generate an approximation. Let's see what that says. Log of 70 divided by the log of 84, and that gives us about 0.959. So we're saying x is approximately 0.959. Now, if it were me and I were being assessed on something like this, I would take what I think is the answer and sub it back in and see if it satisfies my initial equation. So I'm going to take that 84 and I'm going to raise it to and I'm going to use that handy dandy trick of calling the last answer second answer and see what I get as a result. Oh, 70, yay, I have the correct answer. Okay, so this is one way of handling this equation. Another way of handling this equation would be to just take a common log or a natural log of both sides of the equation. And when we do that, we could say like ln of 84 to the x is equal to ln of 70. Okay, which is great. All right, so now I'm going to use the power rule that we discussed up here, where we take a power and pull it out front. So we're going to take this x and pull it out front. X times the ln of 84 is equal to ln of 70. Okay, so what I have is x being multiplied by some value, ln of 84, which is truly a value, although it's hard for us to see it. and that's equal to another value. So I want to isolate x by dividing by that ln of 84. So x is equal to the ln of 70 divided by ln of 84. Okay, so notice that these two ratios, they both have log of 70 over log of 84. One is a common log, one is a natural log, but when you divide them, you do get the same result. Okay, so two different ways of handling this equation. For the remaining examples, I will only use one. All right, so looking at this next example, e raised to the t is equal to 1,000. Okay, so we want to get this t by itself. So I want to take a logarithm of both sides, but I want to take the right logarithm of both sides. So what can I do to get this t by itself? I'm going to take a logarithm with a base of e on both sides. And I think that that is otherwise known as ln. So here we have ln of e to the t is equal to ln of 1,000. Now when I do this, that ln and that e cancel out because this is log base e of e raised to the t. So this is just t is equal to ln of 1,000. Which is an exact answer. We can pull the approximation from our calculator, and that is 6.908. 6.908 from our calculator. Always a good idea to take that back and sub it in our initial equation and verify that it is indeed correct. Okay. Moving on, let's look at this next example. 15 raised to the 4x is equal to 30. Okay, using the same things that we have done before, this time we see that our exponent has something other than just one variable, but we'll handle that when we get there. Okay, so let's start with taking the log base 15 of both sides. Log base 15 of 15 to the 4x, and that is equal to log base 15 of 30. Okay. So on our left-hand side, we have this log base 15 and this exponent with the base of 15, so they cancel each other out, and I am left with, I believe, just 4x. 4x. Now I'm going to write this as with the change of base applied. So 4x is equal to log of 30 divided by log of 15. All right, so now I want to solve for x, so I want to isolate the x. So a couple of different things you can do here. You can, as you're very used to, divide by 4. So I can divide both sides by 4, and that there's nothing wrong with that. But that does introduce the complex fraction of log of 30 divided by log of 15, all divided by 4, which is kind of messy. So I prefer things a little neater. So instead of dividing by 4, I'm going to think of it as multiplying both sides by 1/4. Oops. Okay, so when I do that, that 1/4 and the 4 cancel out, and I do have x is equal to. And remember, when we multiply fractions, I can multiply straight across. So log of 30 times 1 is just log of 30. And log of 15 times 4, that 4 does not get multiplied to the argument. It gets multiplied to the whole log. So it's really 4 times log of 15. Okay, so now what I'm going to do is see about finding an approximation in my calculator. All right, so let's do that. Now, when I do this, I'm going to keep my numerator separate from that denominator by making sure that when I put the denominator in, I use parentheses appropriately. So, and if you feel more comfortable, just put your whole numerator in parentheses. And then divide it by the entire denominator. 15. Oops, I didn't put parentheses in front of the, in front of the 4. So we want to go back and add that in there. Okay, so that whole denominator is in parentheses, the whole numerator is in parentheses, and so we end up with, oh, about 0.314. 0.314. Okay, so let's go ahead and put that back in the calculator and double check that it satisfies our initial equation. So let's take 15 and raise it to 4 times our answer. Okay, and look, we get a result of 30. Fantastic. Okay, a couple more examples to look at. Okay, so we have 1,000 times e to the 0.09t equals 5,000. Now this is a little bit different than what we've done before, because before, anything that has been raised to the power has been isolated already. In this case, we've got this 1,000 that is being multiplied to the expression that's being raised to the power. So we want to isolate that first. So the first thing we're going to do is divide both sides by 1,000. Okay, that's an easy step to make. And we have e raised to the 0.09t, and that's equal to 5. Okay, so now we're back to kind of where we were before. We want to isolate the exponent, so we're going to take an ln of both sides. So ln of e to the 0.09t is equal to ln of 5. All right, now that ln and that e cancel out, and I have 0.09t is equal to ln of 5. And then to isolate my t, I'm going to move this over here. We're going to divide both sides by 0.09. All right, and we get t is equal to ln of 5 divided by 0.09. All right, and that would give us our exact answer. We can get an approximation by using a calculator, and I would suggest doing that. Go ahead and get it, sub it back in, and you should see that we have a correct answer. All right, moving on to this example here. E to the 4x minus 5 minus 7 is equal to that 11,243. Similar to before, we have this expression, exponential expression, but we've got this thing hanging on, this -7, which we want to get rid of. So we want to pull that to the other side by adding it to both sides. And when we do that, we end up with this expression e to the 4x minus 5 is equal to, let's see, 11,243 plus 7, that would be 11,250. All right, take a natural log of both sides. ln of e to the 4x minus 5 is equal to ln of 11,250. All right, so these things cancel, and I am left with 4x minus 5 is equal to this ln of 11,250. All right, so we can add the 5 to both sides, and we can divide by 4. And I'm so sorry I did not leave enough room, so we're just going to move up here. So we're going to add a 5 to both sides, and then we would have 4x is equal to, and I'm going to add it out front, 5 plus ln of 11,250. Now it doesn't matter if I put the 5 in the front or the back, but by putting it in the front, I avoid wanting to add it to this 11,250. And then the last thing we're going to do is divide both sides by 4. And we end up with x is equal to 5 plus ln of 11,250 all divided by 4. Okay, so just for kicks and giggles, we are going to put that bad boy in our